Hello, in this video I will demonstrate an advanced analysis of the effect of TP53 mutations on different molecular processes and on overall survival. If you haven't done so already, you should go through the tutorial PDF on the website to give you an introduction into how to do basic analyses in SEMA and how to use the different functionalities here. So here we will analyze TP53 mutations and the overall mechanisms of their contribution to poor prognosis in different cancers. So we're going to choose somatic mutations, TP53. We will add that to the model. Let's visualize first its mutation frequency across all the cancers. For that, we just click on it, plot selection, select all the cancers that we want to look at, choose proportion, because now this is just showing total numbers, and now we're looking at proportion. So 1 is 100%, so 80%, 60%, so on and so forth. We can just look at mutations here, and now we see that TP53 mutations are most frequently seen in colon, esophageal, head and neck, lung squamous, ovarian, pancreatic cancers. Let's look at the effect of TP53 mutations on overall survival, which is clinical. Overall survival is automatically populated here, but also you can choose other variables, so we're going to go with overall survival. Let's make a hypothesis that TP53 mutations affect overall survival, evaluate it, and overall, so as you can see from the thickness and the color of the line, TP53 mutations correlate positively with clinical outcome. Now in this case, when we're dealing with overall survival, positive correlation means poor survival. So correlation TP53 mutations, TP53 mutations with poor survival or death rates, positive correlation with death rates, and hence poor survival in overall in average. But you can also look at individual ones. And we can overlay it with a z-score over the p-value. So let's select this link, plot the selection. This is showing Kaplan-Meier curve of correlation of TP53 mutation with overall survival in all cancers combined, but stratified by their mutation status. We can also look at individual statistics. So let's look at the z-scores. Now again, this is showing the z-scores of correlation of TP53 mutation with overall survival on the y-axis with all these cancers. And we see that there's a positive correlation in many cases, including in head and neck, the 3 kidney cancer types, in AML, liver cancers, in thymomas, and in uterine carcinomas. In a couple of cases, it correlates with better survival, especially in GBM and in low-grade gliomas. So we can very quickly analyze how this is happening. Why is TP53 mutation correlating with better survival in GBM? So let's very quickly go to GBM. And we see a blue, so it's basically showing better survival. So let's do exploratory analysis to analyze this. So select both, click on global correlates. So what you see here is the correlates of this data type, RPPA this time, in bladder cancers with TP53 mutations and with overall survival. So these are the names of the correlates, so the names of the proteins in RPPA. So we have 1433, beta epsilon zeta, 4-BP1, phospho 4-BP1, and so on and so forth. And this is just their average value in all the patient samples in bladder cancer. And this is the correlation R value, Pearson R value with TP53 mutations. And here you have the Cox regression t-statistic of correlation of this of each one of these with overall survival. So we're looking in GBM, and we're looking, let's say, first let's look at mutations. So what mutations are correlating with TP53 mutations and with overall survival that might explain the positive effect of TP53 mutations on the clinical outcome? So let's look at things that positively correlate with TP53 mutations. So here, TP53 mutations obviously itself is first, but the next one is IDH1. It's also frequently mutated in GBM, so here's the frequency right here, it's 5%. And next is we have this ARH gap, but it's only observed in 1%, 1.6%. We're not really interested in that. In fact, let's put a filter here. So let's say we're only interested in things that are observed in more than 5%. So, and we're only interested in things that negatively correlate with survival, because we're looking for things to explain the negative effect of p53 on overall survival, and we end up with just a handful of genes. Here, p53 mutations very strongly positively correlate with IDH1 and ATRX among these, and these also predict better survival, and they're also frequently mutated. Let's import both into the model. Now we're going to do mediation analysis. Now, the p-value of direct correlation of p53 mutations with overall survival is 0.004. Now we're going to see if adding these variables is going to explain this correlation. So the way we do that is, again, so we add these variables between these two, and while still retaining this direct link. So if after this analysis this link still retains its significance, that means that p53 mutations have an effect on overall survival that is independent of these two variables. But if we lose the significance here, and instead the significance is transferred now to these two paths, then that will indicate that the inclusion of these variables explains the effect of p53 mutations on overall survival. Let's evaluate this model. And as we expected, and the inclusion of these two variables almost completely explained the effect of p53 mutations on overall survival, because now the p-value increased from 0.04, from 0.004, a very significant correlation, to an insignificant one, which is 0.095. And instead, now we see that IDH1 mutations, the p53 mutations, positively correlate with IDH1 mutations, and IDH1 mutations are actually the ones that predict better survival in gliomas, in both GBM and let's look at low-grade gliomas, and in low-grade gliomas too. So now the p-value is pretty insignificant, and now look at these very thick red and blue lines here. Let's just see. So by clicking, we just click here, choose low-grade gliomas here, plot selection, choose raw data here. We're just looking at how p53 mutations and IDH1 mutations co-occur in low-grade gliomas. So as you can see, the red portions are IDH1 mutations in wild types and in p53 mutants. When p53 is mutant, almost all of p53 mutations, 92% of p53 mutant samples also have IDH1 mutations, whereas only 58% of p53 wild-type patients have IDH1 mutations. Let's look at GBM. In GBM, this is even more significant. Only 1%, slightly more than 1% of p53 wild-type samples have IDH1 mutations, whereas 19% of p53 mutants have IDH1 mutations. So there is a very significant correlation, and IDH1 mutations predict much better survival. This is in GBM and in low-grade gliomas. So that was the reason why we see the correlation of p53 mutations with better survival in these two tumors. But this was just a demonstration of how to explain or how to do exploratory analysis to explain certain observed phenomena. Now let's remove these. They're not relevant for the others, so let's just reevaluate, go back, choose z-scores, and let's just go back to that initial plot of the effect of p53 mutations on all the other cancers. So let's see how p53 mutations, the mechanisms, let me say, how p53 mutations affect overall survival. So first let's do a confirmatory analysis. Let's test the hypothesis that that effect of p53 mutations on cell cycle progression, the best studied and best known target of p53, in this p53 mediated poor outcome. So Let's add some of the cell cycle markers: CCNB1, cyclin B1, PCNA, KS67, some of the best known markers of cell cycle progression when you're doing RNA-seq. And let's do a factor analysis. Now we're going to load our cell cycle factor with these three genes, turn it back to causal, and we're going to put cell cycle in between P53 and the overall survival. Let's evaluate. And so here, so what we see is these three thick red lines, which shows that the cell cycle factor has been very well loaded, very well explained by these three variables, and the effect of cell cycle progression on overall survival. A very let's go back to average here. A very well-known effect. So the higher the cell cycle, the worse survival. So let's just plot and see how that holds across cancers. And yes, pretty much in most cancers, higher cell cycle correlates with overall survival. We can also look at it as a Kaplan-Meier curve. So we can play with the cutoff for cell cycle factor. As you go higher, the separation is higher, as you expect again. So higher cell cycle correlates with worse survival overall. Let's go back to z-scores. Now let's see how about this direct effect. Has that been affected? And yes, so previously we saw that P53 mutations had a significant effect on overall survival in the 3 kidney cancers and in liver cancers, but those now disappeared. So almost disappeared. And let's go to let's say liver cancers. So here the effect is pretty much gone. So now the effect has been transferred to cell cycles, which basically means that the effect of P53 mutations on overall survival in liver cancers and in the 3 kidney cancers was due mostly to the effect of P53 mutations on cell cycle progression. So when P53 is mutated, the cell cycle becomes deregulated, and and that contributes to the poor survival in liver cancers. But how about the others? It didn't seem to affect uterine carcinomas, thymomas, AML, and head and neck cancers. So let's first look at uterine carcinomas. Let's remove cell cycle. We're not going to be dealing with that anymore because that does not explain. So cell cycle does not explain the effect on uterine carcinomas and in AML. So let's go to uterine carcinomas. Let's do the same mediation analyses. Let's go to uterine carcinomas here. We're looking at all the correlates. Let's first look at things that negatively correlate with P53 mutations and negatively correlate with overall survival. So here we're looking at RPPA. AKT phosphorylation negatively correlates with P53 mutations, but here we have estrogen receptor. And we know that gynecological cancers can be classified based on the estrogen receptor status, ER positive or ER negative. And ER positivity here, or high ER alpha protein levels, correlate with significantly better survival. So negative here means better survival with overall, and it is very significantly correlating with P53 mutations. Let's look at RNA level. And here too we see estrogen receptor at the top of the list, that both very negatively correlates with overall survival. Again, that means better survival, and very negatively correlates with P53 mutations. So let's choose that and import that to our model. Let's include that here and evaluate. And yes, so when we include that in the uterine carcinomas, now the effect of P53 mutations on overall survival disappeared, and instead it's been transferred here. So let's just click on that, plot selection. Let's go to uterine carcinoma, choose raw data, And yes, show all data points. And when P53 is mutated, the estrogen receptor expression levels are quite low. And estrogen receptor status very well predicts better survival in uterine carcinomas. So that the negative correlation P53 mutation with estrogen receptor status explains the positive correlation of P53 mutations with poor prognosis in uterine carcinomas. And we can see this also as a heat map. Let's choose uterine carcinomas. So yes, P53 mutations are mostly confined to the estrogen receptor negative subgroup, or let me say estrogen receptor negative subgroup is mostly confined to the P53 mutant subgroup here. So, although not completely, but most of it is there. Okay, so let's see if that affected any of the other cancers. Choose z-scores. Let's look at everybody else. What happened here? So here, uterine carcinomas, the effect of P53 mutation on overall survival in uterine carcinomas disappeared, but it didn't really have any effect in thymomas or in AML or in the others. So that was just specific for uterine carcinomas. Let's remove that. Let's move on to thymomas, where the effect is still strong. Let's do the same analysis here. Thymomas. So we're looking again, let's look at RNA level. We're looking at things that negatively correlate with P53 mutations and negatively correlate with overall survival. And here too, let's restrict this to very strongly negatively correlating genes that with overall survival. And here we end up with several genes here, and so we have CYP20A1, POLH, ARIH2, and so on. So the strongest candidate here is POLH, because that also very strongly negatively correlates with overall survival. Let's import that into the model, and let's see if that explains. And yes, it does. It does explain the effect of P53 mutation on overall survival. But then, what is POLH? I mean, is it known to be regulated by P53, or is it a legitimate target? So to check that, we can just click on this link and plot the z-score of correlation of P53 mutation with POLH across all the other cancers. And in almost every case, POLH is strongly negatively associated with P53 mutations, meaning that it is generally suppressed when P53 is mutated in different cancers, probably making it a legitimate transcriptional target of the P53 tumor suppressor. And when we look at the literature, it actually happens to be true. POLH, which codes for DNA polymerase eta, is actually a P53 target gene, and the POLH is involved in DNA damage repair. And in thymomas, we see that the regulation of DNA damage repair or its deregulation when P53 is mutated contributes to the poor outcome in thymomas, as you see here. So the P53, the POLH is also when it's expressed, it would predict better survival. But since it's suppressed here, it predicts worse survival. Let's go to thymomas, plot that raw value. So yeah, high values in POLH predict better survival, and hence negative correlation here. Let's see if that affected any of the other cancers, or if it's specific to thymomas. It does seem to be specific to thymomas. So the contribution of POLH to P53 mediated tumor suppression seems to be specific to thymomas, although P53 does regulate POLH in all the other cancers. Now let's move on to AML. Remove that. Let's go to AML, let's go to ML here. So here we are first. Let's look at mutations. So maybe it is something that has to do with mutations that co-occur with P53. So when we look at P53 co-occurring mutations, we don't really see anything that is significantly mutated. So the only thing is TP53 mutations, and those are only observed in 1%. That's unlikely to explain the effect of P53 mutations. And those that negatively correlate with P53, yes, they are frequent, but the correlation is not strong, and these mutations don't seem to be correlating with overall survival anyway. So again, these are unlikely candidates to be the mediators of P53 effect on overall survival in AML. Let's look at copy number changes. Let's look at things that are whose loss positively correlates with P53 mutations. So now these values show Pearson R values of copy number changes with P53 mutations. So when you see a positive sign here, that means that their copy number gain correlates with P53 mutations. When you see a negative sign, it means that copy number losses correlate with P53 mutations. And so we see several genes here, and which also happen to be predicting better survival. So let's just choose one of these to see if that will explain the effect of P53 mutations on overall survival. So now when we look up this gene and many of the other genes that we just saw in that list, in the top scoring list, they happen to be all on chromosome 5. And chromosome 5 is frequently lost in AMLs and in other myeloid malignancies, and we can actually visualize that here. It's frequently lost in many cancers, but specifically in AML, choose AML here, we see a shallow loss. And in fact, yes, chromosome 5 loss is usually with just one copy of it, so it's called chromosome 5 monosomy in myeloid malignancies, and that is frequently seen, and our analyses indicate that P53 mutations significantly co-occur with that. Even before analysis, we can just visualize that, and that is true. So the loss of chromosome 5 seems to be almost exclusive, to be almost exclusively occurring in P53 mutant subtype of AML. Evaluate. And yes, so although the direct effect of P53 mutations on overall survival that is independent of chromosome 5 loss is still significant, but it is significantly, the significance is substantially less now that we included the chromosome 5 loss. And chromosome 5 loss predicts worse survival in AML. So here it's pretty obvious, and since that positively correlates with P53 mutations, that contributes to the positive correlation of P53 mutations with overall survival. But now there's obviously another player or players. Let's analyze those. Now we're gonna do a global correlation with all three of them, and I'll explain to you why. So here, now let's look at RNA. We're looking at things that correlate positively with overall survival. Let's restrict it to that. Only things that positively correlate with overall survival. Things that positively correlate with P53 mutations, but things that do not positively correlate with chromosome 5 loss. So we do that to remove the confounding effect of the things that correlate with the chromosome 5 loss, but specifically correlate with P53 mutations and with overall survival. So that leads us to these three genes at top that both very strongly correlate with P53 mutations, but also strongly correlate with overall survival, and do not necessarily correlate with chromosome 5 loss. because again, so whatever the other factor in this model is, it has to be something that does not strongly correlate with the chromosome 5 loss, because chromosome 5 loss does not completely account for the effect of p53 mutations on overall survival in AML. So let's import these three variables. Now, when we analyze this, we now hypothesize that these three are targets of p53 mutations, and that p53 mutations contribute to clinical outcome through these pathways. But that will suggest that these three are legitimate targets of the p53 mutation, of p53 mutations in cancer. So let's check that first. Evaluate. In AML, yes, all three are very strongly upregulated when p53 is mutated. But let's look at them in other cancers. We're looking at CSF1 right now, and yes, in at least 6 cancers: bladder, these 4, and in uterine carcinomas, p53 mutation does increase the levels of CSF1 RNA. Let's look at the others. In 3 cases, for GJB5 and for FHL2, again in 3 cases. So CSF1 is by far the strongest candidate here. So for now, I'm gonna remove these, and I'm just gonna retain CSF1, because that seems to be a legitimate target of p53 mutations when I analyze it. Yes, so now including CSF1 significantly reduce the significance of p53 mutations on overall survival, meaning that regulation of CSF1 expression in p53 mutant cancers contributes to the poor survival in AML. And again, as we shown previously, the CSF1 does seem to be a legitimate target of p53, and we know from literature that CSF1 receptor expression has an oncogenic role in the progression of AML. So this analysis demonstrates. We're just going to look at the heat map. Now this analysis just demonstrates the exploratory analyses and factor analysis in mining for mechanisms to explain some of the observed correlations among the clinical and molecular variants in the cancer genomic data sets. And here in a heat map, we're looking at AML. You can see that TRIM36 loss, the chromosome 5 loss, almost always co-occurs with p53 mutations, and CSF1 RNA, high CSF1 expression also is restricted to the p53 mutant tumors. We can also look at a little bit. We can select just these two, and we're just looking at that region of the heat map. Just a little feature that is pretty helpful to zoom in to specific regions of the heat map. Okay, so that was a demonstration of an advanced analysis of p53 mutations and of their mechanisms in different cancers. Thank you.